this afternoon's session is Professor Boulton from Heriot-Watt University with a slightly shortened title, and these bounds for the eigenvalues of the Dirac operator, please.
Thank you very much. Maybe I should start by explaining why I've dropped the word certified from the title of my talk. It hasn't changed, it's just that I could not fit the with this font the title in one line. It looked ugly, so I just dropped it from the title, but it's there, okay? And I would like to talk about bounds, about how to produce bounds for the eigenvalues of Dirac type operators, and in a way that we can calculate these bounds numerically. Okay, so these bounds should be computable numerically. I have carried out this research in collaboration with several people. I will mention that those involved in the research whenever appropriate. And so it's fairly well understood that understanding the eigenvalues of the Dirac operator, trying to find a bound for the eigenvalues of the Dirac operator, it's a challenging. The reason for that is the existence of the Dirac sea that Eric mentioned earlier on. I want to illustrate to you, begin the talk by illustrating to you a situation in which this happened with a simple example. Before I start, I want to just to mention that if you see some of the vertical bars, they look green rather than purple. I think this is a consequence of me typesetting the document in Mac, in a Mac OS system, and this is a PC. So I apologize for that. I can do nothing about it. Okay, so I would like to consider a very, very simple model, the model of the Coulombic Dirac operator, one particle, and I've written it as D, which is exactly the same operator as Eric mentioned in the second slide in his talk, assuming that B is the purely Dirac potential, purely Coulombic potential. So there is no magnetic field involved in here. And I have radially reduced the operator using the spherical reduction. I will talk more about the proper settings of the operator later on. For you, right now, it's just the operator which in matrix forms acts on the space H10 of two spinorial components. The parameter gamma, which belongs to the potential, is so the atomic number times the defined structure constant. I'm assuming it is less than square root of 3 divided by 2. It's a small parameter, different from 0 and positive. And kappa, here is the wave number. I will fix kappa equal to -1. I just want to show you a little experiment with this very, very simple model. The ground eigenvalue is achieved whenever kappa is equal to -1. We can compute all of the eigenvalues of this operator. This is well studied, and they dates back to over 70 years ago, the calculations of these eigenvalues. And so EJ is the correct expression for all of the eigenvalues. They are all positive. They accumulate at the point 1. The essential spectrum of D is, as Eric mentioned earlier today, it's the same as the case of the three-dimensional model. For this one, it's -infinity, -1, 1 infinity. So that's the spectrum of the operator whenever gamma is equal to 0. The free Dirac operator, we can calculate it exactly. And this is a small perturbation of that. So all of the eigenvalues are inside this gap of the essential spectrum. I want to consider the following wave function, trial wave function, and calculate the energy for that. Consider a Gaussian type function phi and psi, the wave function. I put phi and 0. This belongs to the positive part of the spectrum for the free Dirac operator, for the case gamma equal to 0. Yeah? And I calculate the energy. If you have the intuition of the Schrödinger operator, what would happen is that the energy can never be below the ground eigenvalue, of course. This energy comes from our spectral decomposition of the free Dirac operator. But look at what happened whenever we turn on the parameter gamma. So this is the exact calculation of the energy. It's just a calculation. And if A is not too small, it's fairly large, this A and delta are parameter, then this energy can be negative. Actually, it can be arbitrarily negative. So this is a difficulty that you never see for the Schrödinger operator. Whenever, so you calculate the energy, should always be above the ground eigenvalue. Of course, the reason for this is that the problem is strongly indefinite. All the difficulties involving so calculations or rigorous arguments for bounds of the Dirac operator come from this type of phenomenon. I've chosen this basis in a special way. I will argue why I'm choosing this basis in the next slide. So you see, and it's just a calculation. Okay, so let me develop a little bit more this example, and so let me tell you this is a little bit more disturbing. So now I'm considering two wave functions, W1, the same as before, and a wave function which is obtained by kinetic balance application on phi. Okay, so this is purely on the second component with this condition, which is the correct kinetic balance condition whenever we have the radially reduced Dirac operator. So remember the definition of the phi here is of Gaussian type. This type of basis is the one that the chemists use, or it's within the class of the one that the chemists use for calculation of eigenvalues using what they claim is a method which is fairly certified up to numerics, let's say. And so it's very important because it's the one, so it belongs to the class that it's used in packages for computing stuff with Dirac operator, also with Schrödinger operator, okay? So let's compute the extremer of the corresponding energy in the span of these two wave functions, and let's look at what happened with this extremer. So what I'm doing here is applying the so-called Galerkin method with a basis comprising on a two-dimensional test space. And it's the span generated, so the space generated by these two wave functions gives me two eigenvalues, and these are the, so this is what we can say about these eigenvalues. They are the eigenvalues of this matrix. It's just a calculation. The determinant of this matrix for delta small happens to be negative, for delta large happens to be positive. The trace is always negative. So it has two eigenvalues. And in fact, the negative eigenvalue can, if we if we peak delta in a suitable range, the negative eigenvalue crosses the actual gap. So this phenomenon can be implemented. So this is a phenomenon that it's similar to the one before, but now we have a basis which has been used in practical calculation. Of course, this is not rigorous at the moment, so this practical calculation use has been well tuned so that you don't get this phenomenon. But you see, I'm applying the Galerkin method and I'm producing something that is not connected with the eigenvalues. This is the message. This is a natural basis to choose. And the claim, which we've done some research on this, so Nabil Boussaid and Mathieu Lewin are involved in this at the moment with me, is that if you consider a basis of kinetic balance pairs in this way and somehow produce an orthogonal sequence, an almost orthogonal sequence of this basis, you will be able to produce pollution with a basis which is complete. So you will be able to produce a full set of eigenvalues in the gap of the essential spectrum, which would have nothing to do with the actual eigenvalues of your problem. So there is a substantial amount of research, notably maybe the paper by Lewin and Serret on this, on trying to find conditions on a basis so that you can apply a projected method, a projected basis method, which is guarantee, which would not give you this phenomenon, which would provide exact, certified calculation of the corresponding eigenvalues. So I would like to speak about some method which involves so some other different approach as this one. I would like to talk to you about methods which do not depend on the basis. So I would explain how they work later on, but let me just show you the model upon which I would like to apply this method. So for simplicity, I consider the radially reduced one-particle Dirac operator on an external field. As I mentioned, now let me be a little bit more rigorous about the operator itself, about the model I want to tell you. This is a toy model. Our techniques apply to more general potential, but I want to fix ideas. So this is the one I would like to consider for showing you examples. So it's radially reduced, namely the potential has some spherical symmetry. It's purely electric, if you want. There is no magnetic potential, and it comprises the expression. It reduces to the expression d above, with kappa being a wave number in this range. So it's always an integer within a range. This realizes all of the possible decoupling, decomposition of the operator d. And on the potential b, I'm going to assume minimal conditions for self-adjointness of the operator in the L2 space, domain, just the H1 space with Dirichlet boundary conditions at 0. I need that because I have a singularity in the free Dirac operator. The essential spectrum being just the one of the free Dirac operator as well. I'm assuming nothing about whether we have embedded eigenvalues or not, but if you want to fix proper conditions of the potential, this is the classical one. I assume regular potential such that it's dominated by the Coulombic one. Under these circumstances, you have the spectrum given, the essential spectrum given by this, and eigenvalues can appear. So, as a remark, all I'm saying here can apply to much more complicated Dirac operators with or without symmetries. These are general techniques which tell you something about the eigenvalues. Okay, so let me tell you how to. So I would like to devote 2 slides to the classifications of these techniques, which I will tell you just later. So the problem itself, if you want to sort of have a philosophical view on this, is the following. I give you a test space of the domain of my operator, and out of this test space and the action of the operator on it, I want to extract certified information about the spectrum of D. Maybe this information is not that accurate, maybe it is, but it's mathematically certified, if you want. It doesn't, the method, I want the method not to lie to me saying that, so there might be some eigenvalues, if there is convergence of the numerics, yeah, you are close to the eigenvalues. No. I want if I implement this on a computer, I want the computer to tell me a number which is guaranteed to be a bound on the eigenvalue I'm looking at. And so the whole philosophy on these methods that I'm just mentioning in the next slide is that certain matrix rational function which coefficients obtained from the action of the operator on the subspace give me this certified information. Moreover, this is computable. So I can take my formulation of the problem in matrix form, put it in a computer, and this could be programmable in a given numerical scheme. And the proof of most of these arguments involve spectral mapping theorem arguments. So spectral mapping theorem is all about here. I would mention that just later. So the concrete aim, if you want to fix a more mathematical approach, is the following. I have the eigenvalues for the Dirac operator with eigenfunctions C. I want to find an interval in which my eigenvalue lies out of the test, the trial space L, and maybe I would like to also say something about the corresponding eigenfunction, about the corresponding wave function, all of these being mathematically rigorous. I will not talk about the second aim, but in all of what I'm saying, there is also the possibility, and we've done it incorporating approximation of wave functions. And for the space L, I want minimal condition. I want it to be natural, so physically relevant if you want. There is some sort of approximation involved. But I want it to be as general as possible. I don't want to restrict the subspace L with some special conditions that only apply to particular Dirac operator. I want them to be general so that we can program it, for instance, in a finite element method scheme. Yeah? Okay, so the strategy proper that I would like to present, it's work that has been done by some people in the audience, and this is a formulation of that work. So maybe I would like to mention what's this strategy. And it classifies, or I classify it in two type of procedures, two methods. One of them I call global procedures. They tell me something, and so let me start again. These global procedures works as follow. Given minimal information about the Dirac operator, you can produce a bound. Okay, they do not require an a priori information about your problem. They did use something rigorous about the discrete spectrum. This, what I call global method, I would discuss two of them, and the first one is by far the best method available. The idea is to write in a specialized variational form the weakly formulated Dirac eigenvalue problem, and all of these methods, in a sense, they date back to the work of Schur. So in all of them, what I've seen is that there is a Schur complement approach involved, and there is a bound produced on the eigenvalues by means of this Schur complement realization of the method. Numerically, what I produce is a lambda-dependent eigenvalue problem that tells me something out of a crossing of the eigenvalues through an axis. And so among these methods, so for the Dirac operator, is the so they produce extremely accurate bound, and they are always upper bound. They come from a variational formulation. They are upper bound. They are always above the actual eigenvalue. They are upper bound. Okay, so for this, so the theoretical background of these methods, it's so in the context of the Dirac operator. So the best work available, perhaps, is the work of Dolbeau, Esteban, and Serret. So you can formulate, so they consider a restricted min-max principle, and you can formulate this min-max principle in a matrix form so that you can calculate the eigenvalues of the operator, upper bound for these eigenvalues, from this formulation. And another possible theoretical background for this method, which numerically realize the same as the methods of Dolbeau, Esteban, and Serret, is the one that you can extract from the work by Heinz and Matthias Langer and Christiana Treter on matrix operator theory. So the idea is that they have also a formulation of the problem by a variational. So sometimes it's a what is called a triple variational technique, but the numerical realization of that becomes just the standard. Sorry, the numerical realization of that is equivalent to the numerical realization of the method by Dolbeau, Esteban, and Serret. So I want to point out an interesting paper that I just came across with, is one in which Krauss and Treter apply their method to the Dirac operator on manifolds, and it's quite interesting because I have not seen this application before. So the manifolds have some singularity. If you want to do some proper numerical analysis on this, it's quite challenging because it's a properly singular problem. So apart from this procedure on the class of robust global methods, is the so-called second-order spectrum approach, which was initiated by Brian Davis and Eugene Chagarotsky over 12 years ago. So the idea of this approach is that I give you a test space and I calculate a projected problem. I will mention what's the projected problem and so on later on. But essentially, this problem is a quadratic matrix polynomial problem, which just by one iteration, by one test space, tells you something rigorous about the eigenvalues. How rigorous? It gives you an interval which contains spectrum of D always. It never lies. So, of course, this comes with a price. The price is the accuracy in proper implementation of this method is not as great as the variational formulation. So I will come back to that just later on, but this is another method which is useful, for instance, if you know nothing about the operator you are analyzing. And if you want to produce some a priori information that maybe can be post-processing by other methods, this approach to it's valuable. So apart from the class of global methods is the class of local methods. So one of them that is of current interest is the one I would like to discuss in detail just now. These local methods works as follows. I give you a T parameter in the gap of the essential spectrum. And I look around, trying to capture the eigenvalues which are closer to T. So maybe I want to say something rigorous about the next eigenvalue that I see from the point T. These methods, of course, require some information, namely, I want to know more or less where I am. If I have a T in here, I want to make sure there is spectrum on my left, for example. These methods, that's why I call them local methods. They require some a priori information about the problem, and this a priori information can be produced by either of these two approaches. So the origin of this technique, it's if you want, so classically, it's just an extension of the Temple-Lehmann bound for eigenvalues, the one that you found in textbooks. And so the actual realization of this method, it was given by Mertens and Zimmermann in the 1990s, and some other reformulation of these was produced by Davis and Plum about 10 years ago. So this gives you upper and lower bounds for the eigenvalues, but you need information about your spectrum. So if you want, it's a good balance between the two procedures above. So okay, so let me be a little bit more mathematical. So so I would like to talk about 1, 2, and 3, and I would like to start with by showing you the implementation of the variational method. So how do I calculate eigenvalues for D whenever D is, as I showed, radially symmetric? So let me begin as follows. The eigenvalues, so information about the eigenvalues of D are encoded in this quadratic form. So this is a functional, not a quadratic form, it's a functional on wave functions with only one component. It's lambda dependent, fixing a parameter lambda in the interval -1, 1, and I just have to calculate this expression. In the next slide, I will show you a motivation for that. So essentially, what you want to calculate is a projection. So this characterizes the spectrum of D, and I want to produce a version of that on a finite dimensional space. This version would tell me something about the eigenvalues. So how does it work in practice? I pick a finite dimensional D-dimensional subspace of one component spinorial components in H1 0 of 0 infinity, and then I construct a lambda dependent matrix, A tilde L if you want. It depends on the subspace L. So once I've done that, I calculate the eigenvalue A tilde, an eigenvalue A tilde of A, and this is if 0 happens to be in the let me say it properly. If E tilde is such that 0 is an eigenvalue of this matrix, which is just a discretization of that problem, then this is a guaranteed upper bound on the eigenvalue of D. So this is how it works more or less in principle. So the idea is quite natural. So let me maybe draw a graph in here. If this is the real line where the spectrum lies, so let's say this is the 0 eigenvalue, and so on. If mu j are the eigenvalues of the of A, of the actual of the operator associated to this form, they depend on lambda, and they cross the axis 0 with a slope which is strictly larger than -1. So this is the second eigenvalue of A lambda, and so on. What I'm doing here is projecting to a finite dimensional space, well, what they suggested, and find upper bounds. So this is the eigenvalues of the matrix. So these are the A tilde, if you want. So it depends on lambda. So if I find the crosses of this the cross of this eigenvalue with the axis, this will give me an upper bound for my eigenvalue is 0. For later purpose, notice the following. If I have a lower bound for this eigenvalue, due to the fact that this slope is greater than -1, I could get a lower bound of this of the eigenvalue as well. If I do this in an accurate procedure, so if I do this with a basis which accurately capture the wave functions, I should be able to find a small interval around my corresponding eigenvalue, say ground eigenvalue in this case. Okay, so there is a natural motivation for this. It's the idea of decoupling the system. I would like to just not show these slides because maybe there is no time for that. But essentially, what you do in order to prove that A of lambda tells you something about the spectrum of D is decoupling the system. This is not rigorous. It's just a heuristic approach. You produce an operator LE, which is of Sturm-Liouville type with well, singular type, has a singularity at 0, and you are able to bound. So this operator is semi-bounded below. You are able to bound the eigenvalues of this operator. Since it is semi-bounded below, you can produce the standard techniques for calculation of the eigenvalue out of this. So the arguments just connect with the operator L lambda by standard min-max principles. Okay, so I will not give details of that. So I would like to mention to you some recent work on the convergence of this procedure. So what happens if I capture well with L the corresponding eigenspace for lambda? What can I say about the convergence of the upper bound that I produce in there? This is what we know at the moment. So the idea, so let me formulate it as follows. Suppose we have an interval, say -1 mu, where mu is less than 1. And suppose we count the number of eigenvalues of the Dirac operator in this interval. Let Cn be an orthonormal basis of the spectral subspace for the interval J. So just with corresponding eigenvalue Ej. And suppose we fix a lambda tilde which is less than the ground eigenvalue. It's greater than -1, of course, so it should be in the gap. Assume the following approximation condition for the corresponding eigenfunctions. For the corresponding wave functions, I know there is an uj in the test space such that in the norm generated by the form A lambda tilde, which happens to be positive in this case, suppose that these uj's capture up to an error of epsilon j the wave functions for your Dirac operator. What can I say about how close the upper bound is to the actual ground eigenvalue? I can say that this is improved up to an order epsilon squared. So you might think this is not a trivial consequence of some well-known results. As it happened, this is complicated because it's a lambda-dependent problem. And what we are doing here, if you want, in this graph is the following. We are saying something about what happens in between the discrepancy of these two curves. So we have an hypothesis saying that this discrepancy is closed. As it turns, out of that hypothesis, which is condition little a in the slide, we are saying that this distance should be small. Should be, in fact, and square. So if the eigenspace at this level are approximated up to epsilon, with a residual up to epsilon, this discrepancy is of the order epsilon squared. So this is what I mentioned about the fact that the method of Dolbeau, Esteban, Serre, or Langer-Tretter, it's as good as it gets. It has optimal degree of accuracy. But this is only for upper bounds. How do I find lower bounds for the eigenvalues? And so all of the theory of lower bound for eigenvalues, the modern theory, can be written in the following language. And this is ongoing research with Barrenechea and Boussaid. It's based on the work by Davis and Plum. So the idea is the following. Now I want to consider a local method. I fix t, and I want to look around t and say something about the eigenvalues which are close to t. I do the following. So let me consider the following function f, which depends on an index j, will be the eigenvalues which are closer to t, that's the index j, and L is the spectral parameter. Sorry, L is the trial subspace. T is the spectral parameter here. So let's define fj in the following way. So this is a min-max or inf sub on the test subspace L, which is greater than or equal the distance from the spectrum, the j's distances from the spectrum. Let's say if j is equal to 1, what you are doing is minimizing only on the space L this Rayleigh quotient, which is exactly a Rayleigh quotient of the modulus of d minus t, which gives you the distance from the spectrum, the Hausdorff distance from the spectrum to t. So essentially I'm doing the following. I'm fixing t, I'm folding the spectrum around t, and I'm looking for the smallest eigenvalue of that folded operator. As it turns, this gives you, just by standard arguments, the distance from the spectrum. And a crucial observation for this function f is the following. So, well, firstly, if I stand at t and I look at the height of the function in the interval center at t with this height, you will find at least j eigenvalues of the operator, at least j spectral points in general. So the function can be very high. So this is the j dependency here. So for instance, the function 1 would have at least one eigenvalue. So if I look at the height at t for j equal 1, I would have at least one eigenvalue of my operator. And second observation is the fact that this quantity is computable. How do I compute it? How do I realize that? Well, I consider, so I have to solve the following spectral problem. I have to just look at the variational formulation of this and write it in matrix form. As it turns, it's just computing the eigenvalues of a t-dependent problem which is linear. So fj is equal to nu squared, the square root, if I find, so if and only if nu is a solution of a spectral problem involving a bending term for the Dirac operator, a stiffness, so the standard stiffness term, and the mass term. Usually, for implementation of the Galerkin method, you compute this and that, and then compute some eigenvalues of a problem like this with k equal to 0. What I'm saying here is that if you include that term, you are able to say at least to approximate from above the distance from the spectrum. So Okay, so let me draw a little argument, so a little diagram on how this method works in practice, because after just this definition, it's not clear how to implement it. The idea is the following. Suppose I have E0, 1, and 2. And suppose I have the spectral distance from a point T on the line. And suppose, let's say, I have my, so this is -1 here. I have an approximation F1, which is above the true spectral distance. If you want to try and use these to produce bounds on the eigenvalues of your operator, a natural approach is say, well, let me just find the local minima of F, and they would certainly tell me something about the spectrum. It's something that never lies. I know that in this interval, there are eigenvalues for an operator. There can never be no eigenvalues. So this is one possibility, but it's a very bad one. It's much more. There is a much more accurate possibility, and the idea is to fix T not near the local minimum of F, but rather near the other points, the other spectral points. So the local maximum would do well, for instance. If I fix T here, I can consider the line S minus T. I'm thinking of, sorry, this is T minus S. It should be S minus T. So I'm considering the line T minus S, and suppose I calculate F on a point which is far from the local minimum of F. If I do so, this statement is saying, well, if I project on T, on an interval center at T, I would be able to capture the spectrum. If I wanted a lower bound for this point, certainly, just from the picture, it's clear that this lower bound is better than this lower bound for T. We can actually be much more accurate if we consider a lower bound, which is exactly the crossing between the line T minus S and the line F of T. So there is a theorem in that, and that's the theorem. And this is the corresponding theorem. So this proposition says the following: if Fj is a point which is to the left of this crossing, then you would have an approximation, certainly, of the nearest point to T from the left. So if I fix here T, and then I look at the nearest point in the spectrum from T, this is n minus 1, then an accurate bound will be found just by solving the equation f of s equals s minus t. So I'm saying the following here. So this gives me a certified upper bound for the nearest point from the spectrum. If I have a point T2 minus, which is further away from the corresponding f, so if I stand further away from the corresponding crossing with the line T minus S, then I would get a worse bound on the corresponding eigenvalue. So the proof of this statement is just using the properties of Fj, and the fact that I get better as I get closer to T is just uses the fact that the function Fj is Lipschitz with constant 1, hence these two functions are increasing. Okay? So the observation is that the optimal information that I can extract from L for the spectrum of D is contained by the solution of this problem here. How do I compute that solution in practice? Well, the idea is the following, and this is the formulation that Gerisch, Zimmermann, and Mertin produce. The idea is that you want to solve the following weakly formulated problem. So you consider the following, the problem PT for the parameter T, that is the same as this one. You compute this, so the spectral parameter of this problem is tau. If you compute the corresponding solution to this problem that you can write in matrix form, then the following happens. If tau is an eigenvalue of this problem, then 1/4 tau squared is an eigenvalue of the matrix problem associated to F. So the proof is rather elementary. I will skip it because I don't think I have much time. However, the crucial point is the following, and it's contained in this theorem. If I compute, say, the smallest eigenvalue, the smallest negative eigenvalue of this problem, this is a guaranteed bound for the point in the spectrum which is to the left of T. Just calculate T plus 1 over that smaller eigenvalue. Moreover, this bound gives you, so this calculation gives you an expression for the optimal S, which I can choose from reading from the spectral function and the subspace the information about my spectrum. Yeah? So the important theorem is in here. How to implement it? I just have to compute. I use a computer implementation on this problem, and that would give me the optimal Davison-Plume bound, which I can extract from the spectral distance. Okay, so I'm about to finish. I realize there are, I think, 3 more slides, and one of them is about so what do I do if I want to implement the second order spectrum? So what is it, this second order spectrum approach? The idea is quite close to this Mertin, to the Davison-Plume formulation. And let me just show you a slide on how does this method work, because it's quite crude, but it's quite interesting. It also gives you certified bounds on the corresponding eigenvalues. So the idea is the following. Now I look at the same matrix Q as in the formulation for the spectral distance function, but with a parameter which is non-real. So I consider the matrix polynomial in the spectral parameter lambda. And I calculate the spectrum of that matrix polynomial, which happens to be self-adjoint, so the spectrum comprises conjugate pairs. So these are conjugate pairs around the real line, and the spectrum of that quadratic polynomial is what is called, what they call the second order spectrum of the Dirac operator associated to the subspace L. A crucial remark is the following. If I have a point in this set, the spectral distance in the real part would be less than or equal to the imaginary part of that point. So if I have a lambda solution to the eigenvalue problem for Q, which is close, maybe very close to the real line, then I would have a guaranteed bound on an eigenvalue coming from an interval centered exactly at the real line, centered exactly at the real part of lambda. So this method, if you want to implement it, works as follows. I fix a finite dimensional space L. I compute the eigenvalues of a certain matrix polynomial, which is given in here, given by the polynomial Q, involving D. And I find the points of this, in the spectrum of this quadratic polynomial, which are close to the real line. The closer they are, the better they give me an approximation of the spectrum. So let me show you how does it work in practice. So for instance, in here, I'm considering L. So this is a picture of the spectrum of one such a quadratic polynomial. For the case of V being Coulombic potential with alpha equals 1/2 and kappa equals -1, the test subspace I'm picking to be coming from Hermite polynomial times a Gaussian of odd type, so that I have a Dirichlet boundary condition at 0. Balance in the sense that I need a 2-spinor basis, so I consider the same amount of basis elements in the first and the second component. The dimension of the space is L. So how does the method work in practice? So this is just an illustration of what the second order spectrum of the Dirac operator looks like for the test space L. And so a zoom of this picture we can see in here. In black, I've depicted the essential spectrum, the corresponding eigenvalues, starting with the ground eigenvalue. These points are in the spectrum of this quadratic matrix polynomial. As I increase the dimension, they get closer and closer to the real line, hence provide a bound on the so they provide an interval in which the eigenvalues lie inside. So this is more or less the idea of this procedure. So as I did for the case of, yes, so can I have about 2 minutes or I should stop? 1 minute. Okay, so there are convergence results for this procedure that I mentioned earlier, the procedure number 3. And the convergence results say that we gain, essentially, let me just show you theorem 7, we gain an order of convergence of epsilon square whenever we capture now the corresponding eigenspace now in the norm given by the Dirac operator. So before we had the norm corresponding to the quadratic form of Dolbeau, Esteban, Serre. This is the norm of the Dirac operator. In practice, this gives an approximation which is worse than the case of the variational formulation. However, it recovers a quadratic convergence rate. Okay, I'll stop here. Thank you very much.
A quick question.
You used that term, sure complement.
Yes.
Now, what is the precise definition of this?
Yes, so if you write the operator in matrix form, then the sure complement you can calculate out of the entries of this generic operator matrix. I can show you an expression maybe in here, because it's written, okay, no, it's not written in here, but the operator associated to the sure complement is this, this L, yes, is this operator. This operator is the operator associated to the so-called sure complement. So it's nonlinear in the lambda parameter. So for Dirac, it comes from the decoupling of the system, but this theory can be generalized to greater extent. You can just think in general matrix with operator entries.
2 by 2 matrix.
Yes, 2 by 2.
15 seconds. It's just a remark. So in our papers, all estimates are two-sided.
Mm-hmm.
So there are also lower bounds, not only upper.
Thank you very much. It's very relevant to this discussion then. Thanks.
Actually, I have also a remark to your first slide, but maybe we can discuss this later because I think this phi 0 is not in the positive spectrum. But
sorry.
Maybe we have to close because the next speaker is already waiting. Thank you very much.